All right, good evening or good morning, everybody. We are going to be going over some of the basics for IR and NMR spectroscopy. I'm not really going to touch on the mass spec because that's not entirely helpful when identifying compounds like what we're going to be doing, especially for the test. Um, this content is pretty much a hard left turn than what you guys are normally used to. Like these are some reagents, these are some mechanisms, these are some concepts on like why electronegativity does this, all that weird stuff. That like you get the idea, you memorize some stuff, right? But for this one, you're actually trying to apply certain concepts to solve a puzzle, basically. And whether you pass this test is whether you are able to understand the puzzle pieces well enough to make an assumption. All right, this is what compound we will likely have. And IR, as you will see, is subject to a lot of ambiguity because it's pretty much only useful for a limited number of things, mainly for identifying functional groups. Other than that, NMR is pretty absolute. And whether you know your stuff or not, like recognize certain patterns, and you can only do that with practice. That's how you'll figure out how to solve some of these problems. There's no easy way to say it. But with that being said, I'm going to go ahead and share my screen. Share. There we go. Okay. You guys should see it now. Okay. So for IR spectroscopy, the big thing I want to reemphasize is that there's a lot of ambiguity because ranges, like you can memorize the ranges. You can't, you have to, like you have to know carbonyl is about 1700. Well, the ranges that we give you are not absolute. You will see it in IR spec as you see, like you might be looking for a 1700 peak for carbonyl carbon, but what if you find a 1678 or you find a 1750, maybe even a 1775? There's a lot of ambiguity. That's just how science works. Sometimes it's just like that. And you have to recognize, all right, that's a really tall peak in the 1700 region. My money's that it's going to be a carbonyl because I see like, I don't know, maybe a carboxylic acid ugly peak, right? So you have to put a lot of stuff together because the simplest solution is most likely the most likely one. Is the most likely one. So like if everything points to being carbonyl, it's probably going to be a carbonyl. The next thing for IR is that tall peaks is what we're mainly looking at. We look for tall and significant peaks. What I mean by that is, this is an example right here. But you see carbon NMR down there, but ignore that for now. Like obviously you see an OH peak over here, right? And you see some maybe like some sp3 high carbons, sp2 carbons, stuff like that. But this stuff right here in this region is not really that significant. Don't get too hung up on it. Even if it's labeled, don't pay too much on it because it could be something really weird, like a carbon hydrogen bond when it's right next to an oxygen as well. They're not always that significant. Like I can tell you right now, this, I don't know what that is. All right. I don't have to because right now that's not what I'm looking for. I'm looking for carbonyl peak. I'm looking for alcohol peak. I'm looking for this and that. Right. Just compartmentalize and organize what you're looking for to make assumptions. All right. All answers point to this. So if you can organize it really well, you can do it really well, you figure it out. All right. So organizing it, well, look for the tall peaks. All right. Ignore all this stuff because you might see some stuff that might throw you off and just don't overthink it. Don't overthink it. Now some real quick notes before I get into the generalized stuff is you can do this first or you can do the second, but aromaticity, there are four things you're mainly looking for. All right, so peaks past 3,000. Oops. Past 3,000. So you're looking for somewhere within the range of 3,000 to 3,200, around that region. Again, the ranges aren't absolute. If you see something, if you see a small sp2 peak at like 3,225, yeah, and you'll see what other substitutes you can make later on. And these peaks are usually going to be your sp2 carbons. Okay. Next, overtones. Overtones are going to be stuff that's right over here. All right, overtones are little squiggly lines. And this is a pretty good indicator because most of the time that is pretty smooth. If it's not aromatic, it's going to be pretty smooth. So if there's some overtone peaks there, good sign. Next are going to be your peaks at 1600 and 1475. All right, and these are your sp2 carbons that are in a ring structure. So like the ones in a benzene ring. All right, and these again, it's a range, and it's not absolute. Like you can see, like on a peak, you can have like maybe 1448, and then maybe 1568, right? If they're marked and they're significantly tall peaks, and you have everything else, it's pretty good bet that you're gonna have an aromatic. And then you have out of plane bending. And this gives you your substitution pattern. So this is like anywhere between like your 700 to 900 region. All right. Now, some notes I want to make. Your sp2 carbon-carbon ring bends, these can be mid-height. Like I said before, look for the mainly tall peaks. There's like, in my eyes, two exceptions where like if you see them and everything else points to it, I would consider it significant. And this is one of them. What I'm saying is, for the aromaticity, you can see how, let's say you have a 1600 peak, 1491, 1464, whichever one of those, right? So if that's pretty much like our 1600 peak, there's no 1700, there's no carbonyl, okay? And there's an OH peak, my money's going to be in alcohol. We'll go over the flow chart later, so don't worry if you're freaking out about that right now. But if I see some overtones right here, and I see some sp2 bends here, well, I have 1600 and some 1475 peak. I don't know which one it would be. I can probably distribute it. And look, these, they're not very high, right? They're relatively mid. So these can maybe go unnoticed, but mid is okay. And the last thing I want to cover is that aromatic rings pretty much have these four features. Now, the top one, the sp2 peaks, are usually going to be swallowed up by an alcohol peak seen in carboxylic acids. So if you have carboxylic acid, and if carboxylic acid, this peak would not be seen. If you have all of the other three, you have an aromatic ring. You don't need like all four at the same time, because if everything else checks out, it's safe to assume that, well, if everything else checks out, then our sp2 bends past 3000, we're probably eaten up. Next thing, actually, that's kind of it. These all should coincide. Like if you're thinking, okay, I have peaks around 1600 and 1475. Does that mean it's aromatic? No, because if I don't see any sp2 bending past 3000, or I don't see any overtones, not likely. Those are probably just peaks somewhere else. All right. Or if there's no how to play bending, not really. There's some numbers you have to memorize. Now, let's go into a little bit of flow chart. So the first thing you should always be looking for is a carbonyl carbon, because half of the functional groups you guys know don't have the carbonyl, and the other half do have a carbonyl carbon. All right. So if I were to restart this, okay, just from scratch, do I have something in the 1700 region? So 1700 should be somewhere around here. So I'm looking for any tall peak in this region. There is none. So if there's no carbonyl carbons, we can move on. Now, some notes before we move on is it's right shifted if it's conjugated. So if it's part of an ester, for example, right? That hybrid looks a little bit something like this, because it can make resonance structures. Like this. So that double bond, that carbonyl carbon, that has the normal 1700 stretch, it has a little bit of C single bond O character. So it's going to right shift a little bit. Okay. Some other notes. This is relatively going to be a unique, like tall peak. It's pretty definitive. It's going to have relatively tall peak. And then again, your range, again, these numbers aren't absolute. You're gonna be looking for 1650 to 1750, anywhere within that range. And again, if you find something even outside of this range I gave you, consider your options. Like if you have an oxygen in your chemical structure. Like if you have C5, H10O, there's there's a good chance you have a carbonyl carbon because you have an oxygen. Where else is the oxygen going to go? It's going to be part of a ketone or aldehyde or whatever. Okay. Now, for this situation, there's another pathway. Like if, yes, I did have a carbonyl carbon, you go the bottom path. But for now, let's look at the top half. So if there's no carbonyl carbon, the next thing you should look for after your C double bonded O is your OH stretch. And that's going to be around the 3,300, 3,200. It's going to be anywhere, well, right here. And of course, I see a pretty big loop. All right. Your OH peaks are pretty much going to be smooth. So yes, we do have it. So yes, we have an alcohol. Ding, 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 ding. This is what we have. All right. For the alcohols, so not carboxylic acid alcohol group or the alcohol OH hydroxy moiety, does not overlap the sp2. All right. It more than likely it's not going to obliterate those sp2 peaks as would a carboxylic acid. This is usually going to be a relatively big and smooth peak. So right back up here, you see a peak that's relatively smooth. There's no jagged point. It's relatively smooth. That's pretty indicative for your OHs. Now, if it was a carboxylic acid, that same loop that you would see for an OH would be pretty ugly. It's gonna be like not smooth at all. It's gonna be relatively ugly. And again, that's if you have a carbonyl carbon. All right. It's pretty ugly. And why? It obliterates that sp2 peak. All right. So if you're looking for aromaticity, just consider the other three options because your first requirement's probably not going to be seen. All right. And this is pretty much the same region, anywhere within like that 3,200, 3,300 region. For the alcohols, you can kind of tell if they're there because it's the biggest peak. It's pretty wide. Like if you look at a peak like this and you say, that's a ketone. Nah, it's study a little more. Hate to break it to you. But the next one is ester. All right. So if you do have a carbonyl carbon, your 1700 peak, and you don't have an OH stretch, so no, let's move on. The next consideration is an ester. Now, for an ester, it's usually what we give you is 1200, around that range. But again, if you have an ester peak, you have a range, 1150 to 1250, right? Anything around that. And if you have a tall peak in that region and you have a carbonyl carbon, you're thinking, oh, could it be an ester? Most likely, because you have a peak there. And if your molecular formula were to have two oxygens, maybe, more than likely it's going to be an ester. Same up here. Now, C single bonded O, that we give you a value of 1100. But again, your range could be like 1050 to 1150. You have to consider your options because if you don't have carbonyl carbon, but you do have an oxygen, you see a peak there, most likely going to be an ether. And if not, you're just going to have hydrocarbon. Hydrocarbon as in like probably an aromatic ring and just maybe some branches or maybe like haloalkane, which we'll get to later if we do have it. Yeah, stuff like that. Now, the next one is actually pretty significant. It's the Fermi doublet. Now, the Fermi doublet is pretty weird because compared to the others, these peaks are relatively pretty consistent. So the numbers you're looking for is 2720 and 2820, right? Now, for these peaks, they're pretty much going to be on the mark. Their range is probably going to be a lot smaller. Like for 2720, anything 2710, 2730, pretty much going to be acceptable. Same thing with 2820, 28, 2800, 2830, whatever. It's going to be pretty small range rather than like 100 wide range is going to be relatively small. Now for these, the things that I've seen is that the range, well, first off, let me write it down. Range is small. The two peaks are usually going to be relatively the same height. Now it can't always be, you can't always tell because maybe the second peak might be partially eaten up by some sp3 peak. Well, I'll show you in a bit later. Um, Now, one note I want to make is that these can also be pretty mid. So like the 1600 and 1475, mid is okay. These don't have to be really tall. Like if they're there, they're there. So this is what I would mean, right? So let's say you had a peak over here, and let's erase everything. Just pay attention to whatever I write in red. So if you have like, just say jagged peak, maybe some water, that's what that peak is right there. And you have like maybe some SB2 peaks, some SB3 peaks. You could have a peak that looks like this. All right, and let's say it was marked. Let's say that was 27 15, right? Would that be a Fermi doublet? If that's the only thing that's marked, well, honestly, I would say so. Because if I have a carbonyl carbon, right, and I see a significant peak right here, well, that second peak is usually going to be the same height. And the second one that's the leftmost, not 9 times out of 10. Half the time, it's going to be eaten up partially by a peak like that right there. Part of it's going to be eaten up. It's all subject to ambiguity because, again, IR spec is not perfect. All right. Consider your options. But right now, as I would see it, from what I know, from what I'm telling you guys, 2720, 2820 is pretty static. And sometimes they can be small, but I would still consider them. All right. And if there's a lack of anything else, just key tone straight up. It's that easy. All right. So that's pretty much all I have to say about NMR. It's practice. Paige and I did a recording. So I highly recommend that you look at that. Now, the next thing I want to talk about is normally you're going to have proton NMR and then carbon NMR, right? Carbon NMR, similar to proton NMR, we're looking at unique coupled, atoms. The only thing I really want to take away from carbon NMR, the number of peaks you have is the number of unique carbons you have. Right? He's gonna teach it, he's gonna go over it later, so I wouldn't overthink it right now. But I'm just gonna go ahead and prime your brain with something like this. So if you have a carbon NMR with let me draw a blank carbon NMR. And if you had a structure like, I don't know, a toluene, CH3. Well, let's label our unique carbons. So there's a line of symmetry right here. I have a carbon right here, A. There's no other carbon like it across the symmetry. And another carbon right here, B. There's no other carbon that's on the same symmetry. You might be thinking, couldn't this also be B? No, because that B that I just drew is not connected to a toluene. It's not chemically equivalent. Now, if I were to kick it up a notch, C, is there any other carbon that's like it? Well, yeah, you have a C right here where it is sp2. It's two carbon, or it's, yeah, two carbons away from a methyl group. Let's do D. Is there another D that looks like it? Yeah, there's another D right here, which is three carbons away from that methyl group. And then let's bring it back to E right there. So right now, what I see 1, 2, 3, 4, 5 unique carbons. Where carbon C and D, we have two types. So that integration, the area under the curve, would represent double the amount of everything else. So I would see 5 peaks. So like you could see something like this. Whatever. The number of peaks, I don't want to give you too much information before he teaches it. So just keep in mind, the number of peaks is the number of unique carbons you have. Let's do one more example. So if you were to have, let's say, no, I'm not going to throw a bad signaling at you. Yeah, no, yeah. All right, let's make that an OH. All right, so you have pentan 3-ol, right? Let's take a look at our carbons. So we have carbons right here, 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 and here. Actually, let's make it asymmetrical. Let's make it a little weird. OH, pentan 2-ol, right? Okay, 5 carbons, 1 alcohol group on the second carbon, right? So let's take a look. Is there a plane of symmetry? No, not really. I don't even look for the plane signature. I'm looking, all right, let me identify a functional group and let's see if there's anything chemically equivalent. So I know the alpha carbon is connected to directly. There's no other carbon like it. So let's go to the next layer, B. So B right there. And now I ask myself, could this be chemically equivalent? And I'm thinking, no. The first B I just labeled is CH2, while the B I just labeled right here to the right, that's CH3. They're not chemically equivalent. So that's, even though they are equidistant from the alcohol, it's a good bet that they're not going to be chemically equivalent. Now the next one, let's bring back D. All right, is there any other carbon that's connected to it, or not connected, but chemically equivalent? Not really. Um, would it be chemically equivalent to B because they're both CH2s? No. They would show up pretty close to each other on proton NMR or carbon NMR. They might show up close to each other, but they would be pretty distinct peaks. Let's bring it back to red. E. E, there's no other carbon like E, so you have 5 different carbons, you would have 5 peaks. If we were to bring back that original equation we had, not equation, example we had, where we had pentan 3-ol, OH here. Let's redo it one last time. So A, the alpha carbon, are there any other carbons like it? No, because this one's directly attached to OH. No other carbons like that. And I also get B, right? That's a CH2 group. I label B. Now I ask, are these chemically equivalent? Do I have to change anything? They are chemically equivalent. They are both CH2s. They're equidistant from OH, right? They're 1 carbon away from carbon A and 2 atoms away from OH. So it's pretty good. Now let's label C. C, is there any other carbon that's chemically equivalent to C? Yes, right here. So these are chemically equivalent. Well, they are both 2 carbons away from our alpha carbon. It's pretty good. They're both CH3 groups and they're both equidistant from the OH essentially. So I would say there would be 3 carbon peaks. That's all you have to worry about, at least for now. Now we get to the nitty gritty stuff, proton NMR. And I will tell you, it is, excuse my language, but it's going to be a bitch to learn. I hated learning this the most, but once I got it, it was easy. It's because again, it's all practice. Once you get the repetition, you recognize the patterns. You know what to do. I see a CH3 group, or I see a 3H that's a triplet. I see a terminal CH3. Or if you see, I know a 9H 9H single peak, it's going to be a terbutyl group. And we'll talk about that later. But the integration is the first thing we talk about. Integration. Now the integration is the stuff you see where it's like your peak is 9H or 3H. This is area under the curve. So if you have proton NMR, like something like this, where let's say you had a triplet, right? The area under the curve, excuse that voice crack, the area under the curve, it's going to be like if you were to integrate, take that area under here, let's say that was 3H, 3 hydrogens, that's how much it's relatively worth. We'll talk more about it as you do practice, but the integration, actually, no, we actually already covered that. Integration's pretty, it's pretty simple. So you can translate like your 3H would be 3 chemically equivalent hydrogens. So that would be like a methyl group, right? Each of those protons on that carbon are chemically equivalent. Or for 2H, you would have a CH2, right? That's pretty simple. Or 9H, you would have a terbutyl group. CH3, 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 and 9H because you have 9 hydrogens that are chemically equivalent to each other. Each of those methyl hydrogens are equidistant to that middle carbon and probably equidistant to all the other groups. Like if this was, let's say, in a simple OH, right? These hydrogens, A, and A, are 2 carbons away from the OH group. They're chemically equivalent. They are pretty much identical. Yeah. And this, I'm going to make a special note, has to deal with the home carbon, whatever carbon it's attached to. Okay. You'll see why I wrote that a little later. The next one is the number of peaks. So this has to deal with like our triplet, doublet, multiplet, quadruplet. And these follow what we call the n+1 rule. All right, so to give you an example, let's say you had a quadruplet, right? Yeah, a quadruplet with a no, let me do a yeah, no. Yeah, with a integration of 2h, right? So that means that the carbon it's adjacent to has n+1 hydrogens. So what I mean by that, so if I were to draw this example, let's do OH, CH2, CH3, right? Ethanol, something we all love, right? This carbon right here, 2H, so we're looking for the home carbon has 2 hydrogens on it, and its adjacent carbons has 3 hydrogens because n+1. Because if you have 4 peaks, right, I count 4, 4 equals n+1, where n equals the number of hydrogens that are on the adjacent carbons. Now, that was a pretty big concept, and it's a bitch to learn, but I'm going to repeat it once again for your notes for you to rewind on this YouTube video, okay? So the n+1, the number of peaks you have equals n+1, where n equals the number of total hydrogens on your adjacent carbons, right? So if this peak represents this middle carbon right here, all right, you have 2H, where, again, the integration refers to the home carbon. It has 2 hydrogens on it, where the hydrogens are coupled with 3 other hydrogens, right? That means if you have 4 peaks, that means, let me erase these. If you have 4 peaks, that means your adjacent carbons have 3 total hydrogens. And that makes sense because that methyl group has 3 total hydrogens. So couple with those hydrogens and show up as a quadruplet. And this has to deal with adjacent carbons. The next piece of information is your location. And here, what I mainly mean is when you have your proton NMR, right, the more left field it is, and you will be given ranges, the more left field, generally, the closer you are to an electronegative atom. Again, you are given a map on what these mean. Like if you have peaks that are within, like I think it's 5 and 7. I haven't looked at the map yet. I think last time I saw it was probably like, I don't know, a year ago. 5 to 7 is going to be your aromatic range. There are stuff that you can pick up on, but I think this is one of the maps that they give you. I don't know. But you're given a map and you can kind of tell, okay, more left field, closer to the electronegative atom. So if you have a peak that's like, let's say the 2H right here, B, right? The 2H with a quadruplet. It's closer to the OH than carbon A over here. It's a lot closer. So it's a lot closer to the oxygen. It's a lot more electronegative connected, I guess. So to show up more left field. All right. 1 second. Okay, sorry about that. Cat problems. Okay. So this is a little bit of a practice problem that I pulled from one of the old 2022 exams where the question asks you, okay, for each hydrogen listed, so A through G, label what kind of peaks they would show up on the proton NMR. Would they be singlet, doublet, triplet, multiplet, all that kind of stuff? All right. So now, okay, if we're identifying that, we're looking at the number of peaks they have. All right. Would carbon A have 1 peak, 2 peak, 3 peak, thus being a singlet, doublet, triplet, respectively? Right. So let's break this down. So let's look at carbon A. Carbon A, we see has an integration of 3H because it's a methyl group, right? So now that I've identified that, what will the number of peaks be? Well, if this is our alpha carbon, our original one, let's look at the adjacent carbons. And that there's only one, this one. How many hydrogens is that connected to? 0. It is connected to no hydrogen. So if we use the n+1 rule, 0 plus 1, A would be a singlet because the carbons adjacent to it has 0 hydrogens. Now let's look at B. Now B might look a little weird because like, oh wait, B is connected to the carbon and it's kind of shown stretched out. It's just a little bit of an optical curveball per se. Well, let's take a look. Okay, so if I know, you might be thinking, well, this carbon that is connected has no other hydrogen, so wouldn't that also be singlet? No, that's the one it is attached to. So if this is our alpha carbon that the hydrogen is connected to, let's look at the adjacent carbons. There's none here, and there's 2 here. So there's 2 adjacent carbons to that alpha carbon. And total, both of them add up to have 2 total hydrogens, both of them coming from the right carbon that I just pointed to. So if there's a total of 2 adjacent hydrogens, well, n+1, 2 plus 1, where 2 is n, that would be 3. So this would show up as a triplet. I think you guys are seeing a little bit of pattern. Let's take a look at C. Now C, let's take a look. This is the alpha atom. All right, nitrogen. Let's look at how many carbons it's adjacent to. This one. So you might be thinking, okay, if those hydrogens are coupled with the adjacent carbons and the adjacent carbons have a total of 2 hydrogens, would this not show up as a triplet? The answer is no. The weird exception, because God forbid, God bless OChem, there's always going to be an exception, right? Coupling does not bypass electronegative atoms, and the 2 big ones are going to be oxygen and nitrogen. Hey, quit that. They're not going to really bypass that. So this, pretty much, you're going to have an integration of 2H because this atom has 2 hydrogens, and is going to be a singlet. Sorry about that. This is the man making the noise. Okay. Again, it's going to be a singlet. It's going to be a 2H singlet because though you would think it would couple with the adjacent carbons, it cannot cross. So now let's look at D. So D, we're looking at the hydrogens on this carbon. Let's label that our alpha carbon, right? So now let's look at the adjacent hydrogens it has. So we know we can't cross this. So those 2 hydrogens will not couple with the 2 hydrogens on this amine group. All right, now let's look over here. This is the only other adjacent carbon. Does it have any hydrogens? No. So there's a total of 0. There's a total of 0 adjacent hydrogens. All right. So 0 being n, following our n+1 rule, equals 1. It's going to be a singlet. Now let's mix it up a little bit. We've been seeing singlets and triplets. Now let's see what will happen if we do this. Okay. E is our next atom that we're looking for, and let's label this our alpha carbon. And how many peaks would it show up, or would it show up as? How many peaks would it show up as? So let's look at our adjacent carbons. Our adjacent carbons are this one and this one. Let's look at the total hydrogens they have. All right. So total hydrogens, well, I see 1 hydrogen right here, another hydrogen right there. Those are the only 2 hydrogens. You might be thinking, wait, this one right here, that's sp2 hybridized. Will it still couple with it? The answer is yes. The ones that it's attached to, it will couple with still. Don't worry. So the answer is 2 hydrogens plus 1, 3, following your n+1 rule. Oh, he's purring now. This is going to be a triplet. All right. And now that we've identified as a triplet, let's finish F and G. Okay. So F and G, let's go and do F. Let's label this our alpha, right? Our alpha carbon with Yeah, with the one hydrogen. So how many peaks will it show up? How many hydrogens does this adjacent carbons have? So let's identify our adjacent carbons. We actually have three. Right? There are three adjacent carbons. Let's count up all of the hydrogens on all of them. So we have three on the bottom, three on the right, and two on the left. So I count a total of eight hydrogens that can be coupled with, plus one. This would be nine. So this would be a multiplet of nine. On the test, if we're asking you straight up to identify them, I don't think we'll ask you how many. Just you can just write multiplet, but obviously if you're doing a combined spec on the test, we expect you to know. Because you're gonna build the structure. So yeah. So let's do G. G is gonna be this alpha carbon. Let's look at the adjacent let's look at the adjacent carbons, right? So the only adjacent carbon is this one. I see a total hydrogen count of one plus one. The first one that I have here being n, n plus one, a total of two. So this is going to be a doublet. Now, let me quiz you guys a little bit. What integration would G have? You can pause the video now because I'm going to give the answer. 3, 2, 1. It would have an integration of 6H because these hydrogens are chemically equivalent to these hydrogens at the bottom. So they would show up as a 6H doublet because they would show up in the same peaks. They would just expand the area under the curve, but it would still show up as a doublet. He's just chilling now. Yeah. So hopefully that sheds a little bit of light. So now let's bring it back to the integration. So the integration to the area under the curve, and most of the time it will give it to you. So like in problem set 8, it gives it to you like a 4H or a 9H or a 3H. It gives it to you. So I'm going to show you the common things we'll see. So if you have a 1H is really easy. That's usually going to be a methine group. All right, and that's what we see right here. This multiplet right here, that would be a 1H integration, right? Because that home carbon only has one hydrogen, right? That's a feature of the home carbons. My bad. And then, and then, man, I lost my train of thought. Okay, yeah, I'm just gonna move on. 2H is also really easy. That's just gonna be a CH2 group. Let me fix that. Do that in red. CH2 group, right? Really easy. There's two hydrogens that are chemically equivalent to each other, and they're on the same carbon. Now, 3H is also really easy. That's just going to be a methyl group, right? Kind of like this methyl group right here. This methyl group, that would be a 3H, a 3H singlet, right? That means if it's a 3H singlet, all right, then, well, okay, what can I tell? 3H singlet means it has three hydrogens and its adjacent carbons have zero hydrogens. That kind of gives me a clue on the integration. Not the integration, the location. 4H, we kind of kick it up a notch, right? So I'm going to draw a little bit of a line right here. So you're going to kick it up a notch. 4H has some ambiguity. It kind of depends on what you're looking at. A common one would be a disubstituted benzene ring, right? We have two substitution patterns right here. And these four hydrogens will couple with each other. Another way is if you have, let's say, any kind of atom here, right? Let's say that was an oxygen. Let's make it an ether. CH2, diethyl ether, CH3, CH2, CH3. Another way you can have 4H is if you have two chemically equivalent CH2 groups. So basically this, but twice, right? So what I'm talking about is these two right here. Those two CH2s, while individually would have a 2H, they are chemically equivalent. So they would show up in the same peak altogether. So they would have an integration of 4H, because that's how many equivalent hydrogens there are. Another one would be, let's do or another example. Okay, real quick, let me finish the chart here. The two situations would be a disubstituted benzene ring or two chemically equivalent CH2s. All right. Now I'm just going to do another example. So if you have a cyclobutane all, just draw a square. OH. I would expand that. CH2, CH, CH2, CH2. OH right here, right? So this atom would be by itself. Is there anything chemically equivalent to that carbon group? No. All right, to go over here, B, is there anything chemically equivalent to that? B, yes, over here, because it is equidistant to that functional group. They're both CH2 groups in the relatively same location. And C over here, is there anything chemically equivalent? No. That is the only carbon that is 3 atoms away from the OH group. Now, how they show up in the NMR? Well, these two are chemically equivalent, and they're both CH2 groups. So they would show up as a 4H, because they're chemically equivalent to, they're two chemically equivalent CH2 groups. The next one's 5H. This one's relatively easier. This one's pretty simple. It's just going to be a monosubstituted benzene ring, right? Where you have H, 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 H. Those hydrogens are going to be chemically equivalent, so they're going to pair up together. Okay. Now 6H gets a little bit weirder. Two situations, you have a geminal dimethyl group. The cat's leaving, I think. Where these two chemically equivalent CH3s would couple together. You have two 3H's, excuse me, two 3H's that couple together. So it's just, that's a bad error. So just two 3H's times 2. Okay. Another reason is if you had 2H's times 3. 3 2H's. So where would you see that? You could see that, like, let's say CH, CH2, 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 H, H, OH, right? These three would have chemically equivalent CH2 groups. So you kind of have to think outside the box a little bit, because C6H could be benzene ring, could be two geminal methyl groups, or it could be 3 chemically equivalent 2H groups, right? Now 7H you'll rarely see. That's not really that common. I doubt you'll see it. 8H, kind of like the pattern over here. I think the only way you can find that is if you have 4 chemically equivalent CH2 groups. So if you had like CH2, 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 and then some kind of other group, whatever. But these are chemically equivalent to each other, because there are 2 CH2 groups, or 4 CH2 groups. So they're all chemically equivalent. So on the Proton NMR, they would couple together. They would just increase that integration to 8H, right? Now let's look at this last one. This one's, we're bringing it back to easy. This one is just most likely going to be a tert-butyl group. CH3, CH3, CH3. It's like tert butoxide. Okay. So tert butoxide, not butoxide, tert butanol, my bad. These CH3s are chemically equivalent. They are equidistant to OH. Each of them have 3H integration, but obviously you put them all together in the same NMR because they're chemically equivalent. They're going to be showing up as a 9H. Just for some speculation, in this one, this would be a 9H singlet. It's a really common one because, well, look at that adjacent carbon. There's only one adjacent carbon. It doesn't have any hydrogens. Yeah, pretty crazy. That's pretty much all I have for now. I might record another video in a little bit, just for some practice, but this should help.